In this video, we study multivariate functions that are functions of many variables. So it will look like something like this. Y is equal to f of x1, x2, and so on up to xn. So in this case, there are n variables. And these are inputs, and y is the output. So this f is a function from the n-dimensional Euclidean space to real numbers. More generally, we might have the codomain as m-dimensional Euclidean space instead of just one-dimensional space. But mostly in this lecture, we consider only these functions from two-dimensional space to one-dimensional space. Just for the sake of simplicity. The idea applies to any dimensions, but there is a huge difference between univariate functions and bivariate or multivariate functions. The reason will become clear later. In this figure, I show the graph of this function. That is, z is equal to f of x and y, where this function is defined by x squared plus y squared. So in this case, x and y are independent variables, and z is the dependent variable. Okay, here we have x and y. So if we fix the value of y, for example, to 0, then we can consider this function as a function of x alone. So let's fix y to 0. Then we have just z equal to x squared. So if you look from this direction, it will look like this. So x and z and something like this. Just a well-known quadratic curve. And if you fix y to another value, for example, 1, then we have z equal to x squared plus 1. So the graph from this direction will look like this. So we shift by 1, and so on. And instead, we can also fix the value of x. So in this case, this function becomes a function of y alone. So let's say we fix the value of x to 0, then z is equal to y squared. So if you look from this direction, the graph looks like y and z be like this. And if you change the value of x to, for example, -1, it will be y plus 1. Then it will look like this. Yeah, the difference is 1. And so on. And so as a whole, the graph looks like this. So it is a surface like this. It's not a line, it's a surface. So this is the case for two bivariate function. That is function of two variables. For this function, the domain is the entire xy plane. That is the two-dimensional Euclidean space. But in general, we might want to limit the domain to some subset, let's say S, of the entire plane. Suppose f is a function from S where S is a subset of two-dimensional Euclidean space to real numbers. And we want to define the notion of limits in this case. That is something like this. Limit of f of xy is alpha. Alpha is of course a real number. When x and y approaches a and b. Okay. For example, in this case, let's say this is a and b, like maybe 4 and -1 and so on. So we pick any point in this xy plane and move this point to AB. Okay? But there are infinitely many ways to approach this point. So what do we exactly mean by this? So xy approaches AB, then the value of f of xy approaches alpha. So this is the intuitive meaning of limits, but we want to define this more precisely. So how can we do that? Okay, let's recall the definition of limits for univariate functions. Let's say we have a function from real numbers to real numbers, or any subset of real numbers to real numbers, okay? Then we say this limit f of x approaches alpha when x approaches a. So what we meant by this was the following. For any epsilon that is positive, there exists a delta that is positive, and for all x in the domain, let's say S, for all x in the domain, if x minus a is less than delta and x is not equal to a, then f of x minus f of x minus alpha is less than epsilon. Okay, so if this is satisfied, we mean that the limit of f of x converges to alpha. Okay, and this was easy in one-dimensional case because in one dimensions, the way the directions from which to approach alpha was just two ways, either from the left or from the right. And this was expressed in terms of this absolute value of the difference between x and a. Okay, so the difference between x and a is less than delta. Okay, then let's write this way, x and a, and let's say this is a function, and when x is somewhere between alpha minus a minus delta and a plus delta. So as long as x is within this range, then the difference between f of, not f of a, but alpha and f of x is between within the difference of epsilon. Okay, so this is alpha plus epsilon, this is alpha minus epsilon. So as long as x is closer than a minus delta or a plus delta to a, the difference between alpha and the value of the function is less than epsilon. So that was the definition. And it was easy because there are only two directions, and this difference can be expressed in terms of the absolute value. So x minus a less than delta. Okay, so how can we extend this idea to multivariate case? In bivariate case, it is a bit complicated because let's say we have AB here. To approach this point, there are infinitely many directions. So it's not just two ways, but infinitely many ways. So to express some point x, y is close enough to AB, we use the idea of the epsilon neighbor. Actually, in this case, delta neighbor, let's say. So that is if xy is in the delta neighbor of AB. Okay, so that means xy is within the circle centered at AB and the radius of delta. So if this is the case, then we say xy and AB are sufficiently close. Okay. So if this is true, then if f of xy minus alpha is less than epsilon, so whatever the value of epsilon, if we can find sufficiently small delta such that if this is true, then this is true. So if this holds, then we say the limit of f of xy is alpha when xy approaches AB. Okay. Approaches AB, f of xy is converges to alpha. Okay, so let's formalize this. So we say f of xy converges to alpha as xy approaches AB if the following holds. For any epsilon that is positive, there exists some delta that is positive, and for all xy that is in the domain of this function, if xy is in the delta neighbor of AB and xy is not equal to AB itself, then the difference between f of xy and alpha is less than epsilon. Okay, so if this holds, then we say f of xy converges to alpha. That's the definition of limits in the case of bivariate functions. But this definition can be easily extended to any dimensions. So because we can always define delta neighbor for in any dimensional spaces. Actually, this definition of limit is almost identical to the case of univariate function, this one, if we adopt the vector notation. So instead of writing xy and AB, just write x vector xy, and let's say A with this wavy underline as AB. So these are just two-dimensional points. So if when we say xy is in the delta neighbor of AB, what this means is that this. But what this really means is just that this point x is within the circle centered at A with radius of delta. So that means the distance between A and x is less than delta. Okay, so what this means is just the distance between x and A is less than delta. But using the vector norm notation, this distance is just x minus A, the norm, less than delta. So if we use this notation, just replace this with, so this means this, so vice versa. They are the same thing. So instead of writing like this, we could write like, let's see, x minus A less than delta. Okay, so if we write like this, it's almost identical to the definition of limits in the case of univariate case. So instead of this absolute value, we use the norm. That's the only difference. So they are essentially identical. And of course, this is a natural generalization of the univariate case, because in the case of one-dimensional space, this is just the same as absolute value. And just like univariate functions, we have the following properties of limits. I will just list without any proof. You should try to prove these, but the strategy is exactly identical to the case of univariate functions. So first, let's say we have two functions, f and g, from some domain to real numbers. And let's say we have limits x, y, a, b, f of x, y is alpha, and limit x, y, a, b, g of x, y is beta. By the way, we can also write like this: f of x, y converges to alpha, f of g of x, y converges to beta as x, y approaches AB. Okay. And so suppose these are given. Okay, then we have the following properties. For any KL, those that are real numbers, we have limit xy approaches AB, k times f of x plus L times g of x, xy. This converges to k alpha plus L beta. Okay, and alpha and beta are the limits of f and g. So this is the first property. And the second property, the limit of the product of these two functions converges to the product of the limits. And third, if beta is not 0, then the quotient f of xy over g of xy converges to alpha over beta. Okay, these properties can be proved in the same way as univariate case, so you should try that. Let's see some examples. Clearly, we have the following. These are trivial examples. So x can be considered as a function of x and y, right? It just happens not to depend on y. So if we take this limit, this obviously converges to a, because if a, x and y approaches a and b, x approaches a. That's trivial, right? And similarly, we have x, y to a, b. Y is a function of x and y. This converges to b. Obvious. So, for example, from this, we can see that any functions of polynomial functions of x and y converges to f of AB. Okay, so f is, in this case, f is a polynomial. Okay, polynomial of x and y. Okay, polynomial means something like this. For example, if let's say f of xy is equal to x cubed plus 2xy squared, then the limit of this function as xy approaches AB is, so just replace x with a and replace y with b. So this is it. Now this can be proved using these properties, okay, especially this one. The limit of a product converges to the product of limits. So that is, so we have this, for example, therefore the limit of x squared is just a squared, right? I mean, these are the same thing. And because x converges to a, therefore x squared is x times x. So the limit is a times a, that is a squared. And similarly, limit of xy is limit of x times limit of y, so that is ab. And we can do this repeatedly, so that the limit of x cubed is a cubed, given this. Okay. So for any polynomial of x and y, we have this relation. Okay. And moreover, if g of AB is not equal to 0, then we have g is also a polynomial. Just assumption here. And in this case, the limit of f of xy over g of xy is f of AB over g of AB. Okay. So, for example, let's say f of xy is the same as before, x cubed plus 2xy squared, and g of xy is 5x squared plus xy plus 3y cubed. So this is a polynomial. This is a polynomial. And g of, let's say, 1, negative 1 is, so this is 5 times 1 plus 1 times negative 1 plus 3 negative 1 cubed. So this is negative 3 negative 1 5, so this is 1. So this is not 0. So the limit of the ratio between f and g when xy approaches 1, negative 1 is f of 1, negative 1, g of 1, negative 1, and f of 1, negative 1 is, let's see, 1, 2, 1, negative 1 squared is 1, so that is 3 over 1, so that is 3. Here is the next example. Consider this function, f of xy, x squared minus y squared, and x squared plus y squared, and consider the limit when xy approaches 0, 0, the origin. Okay, at the origin, both numerator and denominator, they are 0, so it's clearly undefined. It's not clearly defined. And actually, there is no limit in this case. To see this, let's consider so approaching this origin along this line. So y equals to mx, where m is a constant. Okay, so approaching the origin along this line with some slope m. Okay, so in this case we have f of x and mx. So just substitute y with mx. We have x squared minus m squared x squared and x squared plus m squared x squared. So we can get rid of x squared. So 1 minus m squared and 1 plus m squared. Okay. So since this does not involve any x anymore, so this will converge to just this value as xy approaches 0, 0. So this limit, I will enclose with quotes. This depends on the value of the slope m. Okay, so that means the limiting value depends on the slope, and so depending on the way you approach the origin, the limits are different. So that means this function does not converge to any unique value. Therefore, there is no limit in this case. For example, if m is 0, so that is along the x-axis. So when m is 0, y is 0. So we have 1 over 1, so that is 1. So if m is 0, then the limit is 1. Okay, but when m is equal to 1, in that case, we approach the origin from along the y-axis. Then the limit is, let's see, 1 minus 1, so that is the limit is 0. So they're different. So it doesn't converge to any unique value. Now here's another example. Let's consider this function, f of xy, xy squared over x squared plus y squared. And we consider the limit when xy approaches 0, 0, the origin. To consider this limit, let's use the polar form of x and y. That is r cosine theta and r sine theta. In case you forgot what the polar coordinate is, here it is. So for any point x1 and y, we take this distance from the origin as r, and the angle between this line from the origin and the x-axis as theta. Okay, so this is r cosine theta, and this y coordinate is r sine theta. And this is the polar coordinate. And in the case of limits, x and y are not exactly equal to 0 and 0. So we may assume that r is always positive. Okay, so let's substitute this into here. So we have f of r cosine theta, r sine theta equals to Okay, so xy squared, so that is r cubed, and cos theta sine squared theta. And a squared plus y squared is just r squared, right? So so this squared plus this squared is this squared, so it's r squared. That's Pythagorean theorem. And so this is, so we can cancel this r. So this is it. And now we show that the limit is 0. Okay, so f of xy minus 0 is equal to this one, r cosine theta sine squared theta. And this is, let's split this absolute value, r is positive, so just write r, and cosine theta and sine squared theta. But cosine and sine, they are always less than 1 or less than or equal to 1. So this is less than or equal to r. Okay. So as xy approaches 0, 0, we have r approaches 0, right? Because x approaches 0, y approaches 0, then this r approaches 0. Okay, so this converges to 0. Therefore, the limit when xy goes to alpha 0, 0, f of xy, in this case, this one approaches, converges to 0. Next, let's define the continuity of a function. So we say a function is continuous. So this means this, the limit continuous at AB, let's say. This means when xy approaches AB, f of y, xy converges to f of AB. Okay? So if the limit is the value of the function at that point, then we say the function is continuous at that point. And it is easy to see the following properties of continuous functions. So any linear combination of continuous functions, so let's say f and g are continuous, so suppose these functions are continuous at this point. Okay, in that case, any linear combination of these functions k and l are real numbers, real constants. So for example, linear combinations of these functions and product of these functions and quotients of these functions, as long as the denominator is non-zero. So these are all continuous functions. At AB. And we have already seen that any polynomial functions are continuous functions at all points. And the ratio of two polynomial functions is called rational function. And they are also continuous as long as the denominator is non-zero. By the way, any product of polynomial functions are also polynomial functions. And linear combinations of polynomials are also polynomials, so they are all continuous. Next, consider this example. Let's define a function f of x and y as follows. So this is equal to xy squared over x squared plus y squared. This is the function we have considered before. This is defined when xy is not 0, 0. Okay? So, and this function is defined as 0 when xy is 0, 0. Okay. So at the origin, this function is defined to be 0. Okay. Other than the origin, this function is defined to be xy squared over x squared plus y squared. So is this function continuous at the origin? Okay. Anywhere other than the origin, this function is continuous, right? Because the numerator is a polynomial function, so that is continuous. And the denominator is a polynomial function that is non-zero at everywhere other than the origin. So it is continuous. And the ratio between two polynomials, so that's a rational function, that is continuous. At the origin, it is defined to be 0, but as we have seen before in one of the examples we have seen before, this function here, this converges to 0 when xy approaches the origin. Therefore, okay, so limit xy squared x squared y squared when xy approaches 0, 0. This is 0 as we have seen before. But this is actually equal to the value of the function at the origin. Therefore, f of xy is continuous at the origin, so therefore everywhere. So that is the entire two-dimensional plane. It is continuous. Finally, we introduce two helpful theorems without proof. Okay, the one is the intermediate value theorem. The other is the extreme value theorem. Let's call it IVT and EVT. Okay, these are natural extensions of their respective univariate cases. Okay, first, the intermediate value theorem. Okay, let's say we have a function from D to real numbers where D is a subset of the n-dimensional Euclidean space. And also, D is path connected. So as we have studied before, path connected means they are made of one big chunk. Okay, so they are not something like a set of separated regions, but it's just one region, all connected. Okay, and also we assume that f is continuous on the entire domain. Okay, and also we assume that f of A and f of B are different, where A and B are elements of the domain. Okay, let's say A and B. Okay, so they take different values. Okay, in that case, for any value L, intermediate value L, between f of a and f of b, there exists some element of D, let's call it C, such that f of C is equal to L. Okay, so important points are the domain is path connected and f is continuous, and it can take different values at two different points. Then we can always find some point C such that this value, the value of the function at this point is somewhere between f of a and f of b. Okay, so just to recall the univariate case, it was something like this. So we have a function, continuous function, in some path connected region. Okay, let's call it a and b. Okay, so the function must be defined in all these points. Okay, so let's pick any value between f of a and f of b. So let's say L. Okay, then we can always find some point C such that this is equal to f of C. Okay, this is intuitively easy to understand. Since this function f of x is continuous, and also the domain is path connected, so it's not split into different separate pieces. Okay, so this is one piece of the domain. Okay, then there is always a value of x such that f of c is equal to some intermediate value between f of a and f of b. So the same applies to multivariate case. Okay, the other theorem is the extreme value theorem. So that says a continuous function, let's say f is a function from some domain f to real number, where f is a subset of the n-dimensional Euclidean space. And we assume f is also bounded and closed. Okay, and if this is also f is continuous on f, then f has maximum and minimum values. So basically, so these are extreme values. Okay. So this is easy. Bounded and closed means it is defined on something like this. So the boundaries are included in the domain, and it's not infinitely large, so it can be contained in some circle or some hypersphere. Okay, so this is the size of this domain is limited. Okay, it's bounded, and the function f is continuous. So this function takes some maximum or minimum value somewhere within this domain. Okay, let's say C and D, and f of C is maximum and f of D is minimum. So there exists such C and D in the domain F. such that this is maximum, this is minimum. In the case of univariate case, it was something like this. So the function is defined on a closed interval, okay? So including both endpoints, okay? If that's the case, then the function had some minimum value. For example, in this case, this is the minimum value and this is the maximum value, okay? We should emphasize that the domain must be a closed set, okay? Otherwise, for example, what if this is not a closed interval but an open interval? Okay, so in this case, in that case, this endpoint is not, these endpoints are not included in the domain. So therefore, the function in this case does not have a maximum value, okay, because this point is excluded. But somewhere close to this one is greater than this local maximum, so it doesn't have the maximum point. Therefore, the important requirement is that the domain is a closed set. So this also applies to the multidimensional case. So it's bounded and closed. So this is a requirement, in addition to the continuity of the function. Okay, that's all for this video. See you later.